Welcome to our discussion on analysis of variance or ANOVA. We'll explore how this statistical method helps in comparing means across different groups to determine if there are any statistically significant differences. We explore methods for estimating population variance and standard deviation using the chi-square distribution. For comparing variation in two samples, the if distribution is utilized. One-way and two-way analysis of variance are key techniques, with the Tukey test aiding in multiple comparison tests. The sample variance is the best point estimate for population variance, while the sample standard deviation estimates the population standard deviation. We use sample variance to construct confidence intervals for population variance and sample standard deviation for population standard deviation. Additionally, we can test claims about population variance or standard deviation. For a normally distributed population, the chi-square distribution is defined by chi square e equals sign n minus 1 asterisk a square e 20 which degrees of freedom. Typically, degrees of freedom equals sign n minus 1. Unlike symmetric distributions, chi-square values are non-negative and vary with degrees of freedom, affecting confidence intervals. The chi-square distribution is an important distribution in statistics. It is used mainly when we work with categorical data, frequency data, and variance-related problems. One important feature of the chi-square distribution is that all values are non-negative. That means the value of chi-square cannot be negative because it is based on square differences. So the curve always starts from 0 and moves to the right side. Another important point is that the chi-square distribution is not symmetric. Unlike the normal distribution, it is usually skewed to the right. This means the curve rises quickly and then slowly decreases with a long tail on the right side. The shape of the chi-square distribution depends on the degrees of freedom, written as df. When the degrees of freedom are small, the curve is more skewed. As the degrees of freedom increase, the curve becomes wider and moves more toward the right. In this slide, we can see two examples, df equals 10 and df equals 20. The curve with df20 is shifted more to the right compared to df10. This shows that degrees of freedom strongly affect the shape of the chi-square distribution. In simple words, the chi-square distribution helps us test whether observed data are significantly different from expected data. It is commonly used in chi-square goodness of fit tests, tests of independence, and variance analysis. The sample variance is the best point estimate for population variance. Typically, the sample standard deviation estimates the population standard deviation. We can use two sample variances to test claims about differences between two population variants. When two populations have equal variances, the F distribution formula is used. F equals sign S1 quotient. This F score measures relative standing by comparing variations as a ratio. The F distribution requires 2 degrees of freedom. Numerator degrees of freedom equal sign N1 winner 1 and denominator degrees of freedom equal sign N2 winner 1. Unlike symmetric distributions, F values are non-negative and vary with degrees of freedom. The IFI distribution is used to compare variances between two normally distributed populations with equal variances. It requires two different degrees of freedom. Numerator degrees of freedom equal sign N1 winner 1 and denominator degrees of freedom equal sign N2 winner 1. The IFI distribution is not symmetric and values are non-negative, varying with degrees of freedom. We extend hypothesis testing to assess if three or more population means are equal using one-way ANOVA. This involves analyzing sample variances to test the null hypothesis that all means are equal versus at least one differing. This method is suitable for comparing means within quantitative data categorized by one treatment or factor. For a one-way ANOVA, populations should have approximately normal distributions and equal variances, with a variance ratio up to 9:1. Samples must be simple random samples, SRS, of quantitative data, independent, and categorized in only one way. The if test statistic is calculated as the ratio of variance between samples to variance within samples. It is sensitive to sample means. Degrees of freedom differ based on sample sizes. For equal sizes, numerator degrees of freedom is k1, denominator degrees of freedom is kn minus 1. For unequal sizes, numerator degrees of freedom is k1, denominator degrees of freedom is nk. The one-way ANOVA is a right-tail FF test focusing on comparing variances. Importantly, rejecting the null hypothesis doesn't confirm all means are different, nor does it specify which means differ. We will use the performance intelligence quotient scores from table 12.1 and a significance label of alpha equals sign 0.05 to test if the three samples originate from populations with equal means. This involves comparing the means to determine if there is a statistically significant difference among them. Let's examine the summary statistics from the collected data. These statistics provide a foundational understanding of the dataset's characteristics, including measures like mean, median, and standard deviation. Analyzing these will help us interpret the data's distribution and variability effectively. The samples are approximately normal with similar standard deviations. They are simple random samples, independent, and categorized by lead exposure levels low, medium, and high. This ensures the validity of our analysis. We are testing the hypothesis. H0 states all means are equal, while H1 suggests at least one mean differs. The significance level is set at alpha equals sign 0.05. This is the ANOVA result for the performance IQ scores of children in three groups: low, medium, and high blood lead levels. First, look at the mean values. The low blood lead level group has a mean IQ score of about 102.71. The medium blood lead level group has a mean of about 94.14, and the high blood lead level group has a mean of about 94.19. So, from the sample means, the low blood lead group appears to have a higher average IQ score than the other two groups. Now we check whether this difference is statistically significant or just due to random variation. For that, we look at the ANOVA table. The F statistic is 4.071 and the p value is 0.0195. Since the p value 0.0195 is less than the significance level 0.05, we reject the null hypothesis. This means the three population means are not all equal. So the conclusion is there is enough statistical evidence to say that performance IQ scores differ among at least one of the blood lead level groups. However, ANOVA only tells us that a difference exists somewhere. To know exactly which groups are different, we would need a post-hoc test, such as Tukey's test. The p-value is 0.020, which is less than the significance level of 0.05. Thus, we reject the null hypothesis. This suggests that the three samples likely come from populations with different means. Greater blood lead levels seem to correlate with lower performance intelligence quotient scores, though specific mean differences aren't formally concluded. The ANOVA test is right-tailed with larger test statistics leading to smaller p-values. It assumes equal population variance as some quarter. The F test statistic is the ratio of variation between samples based on sample means to variation within samples based on sample variances. This slide explains the relationship between the F test statistic and the p-value in ANOVA. First, we compare the sample means. If the sample means are all close to each other, it means the differences between groups are small. In that case, the F-test statistic becomes small and the p-value becomes large. When the p-value is large, usually greater than 0.05, we fail to reject the null hypothesis. So we conclude that there is not enough evidence to say the population means are different. On the other hand, if at least one sample mean is very different from the others, the variation between groups becomes large. Then the F-test statistic becomes large and the p-value becomes small. If the p-value is less than 0.05, we reject the null hypothesis and conclude that the population means are not all equal. So the main idea is simple. Small f value means large p value and no significant difference. Large f value means small p value and significant difference. Multiple comparison tests help identify where mean differences lie. If the one-way analysis of variance null hypothesis is rejected, we'll focus on the Tukey test, which compares pairs of means, providing p-values to determine if any two means differ. The null hypothesis assumes equality of the means compared. We compared the average miles per gallon for 2000 to 20 vehicles from four manufacturers to identify differences in means. A one-way analysis of variance was deemed appropriate, revealing at least one mean miles per gallon differs significantly, indicated by a low p-value of 0.0003. To pinpoint where the differences in mean miles per gallon lie, we perform a Tukey test. This test compares all manufacturer means two at a time while controlling the overall significance level. It helps identify which manufacturer has a higher or lower mean miles per gallon. This slide shows the Tukey post-hoc test results. After ANOVA, we already found that not all group means are equal, but ANOVA does not tell us exactly which groups are different. That is why we use the Tukey test. Here, each row compares two group means. We check the p-value at the significance level alpha equals 0.05. If the p-value is less than 0.05, we conclude that the two means are significantly different. If the p-value is greater than 0.05, we conclude that the two means do not differ significantly. For the first comparison, mu1 and mu2, the p-value is 0.0023, which is less than 0.05. So these two means differ. For mu1 and mu3, the p-value is 0.2038, which is greater than 0.05. So these two means do not differ. For mu1 and mu4, the p-value is 0.0034. So these means differ. Similarly, mu2 and mu3 have a p-value of 0.0142. So this means differ. But mu2 and mu4 and mu3 and mu4 have p-values greater than 0.05. So their means do not differ significantly. So the Tukey test helps us identify exactly where the differences are. In simple words, some group pairs are significantly different, but not all pairs are different. We explore the two-way analysis of variance, a method for data categorized by two factors. Start by testing for interaction between these factors. Then assess whether row or column factors have significant effects. We extend one-way analysis of variance to two-way analysis of variance to test if three or more population means are equal when data is categorized in two ways. This method compares means within quantitative data categorized by two factors. Using two one-way analysis of variance is insufficient as it ignores potential interactions between factors. Interaction occurs when the effect of one factor varies across different categories of another factor, indicating a synergy. Interaction plots help visually assess this effect. It's crucial to test for interaction effects first to understand the dynamics between factors. For a two-way ANOVA, each cell's population should be approximately normal with equal variance. Samples must be simple random samples, independent and categorized in two ways. A balanced design where all cells have the same number of sample values is used here, though not a general requirement. In a two-way ANOVA, the first test examines the interaction effect. We test the hypothesis H0, no interaction effect, versus H1, there is an interaction effect. The test statistic is F equals sign mean square interaction slash mean square error. If H0 is rejected, indicating a significant interaction, we cannot proceed to test for main effects. The second and third tests in a two-way ANOVA assess main effects for row and column factors. Hypothesis test for the presence of these effects. The test statistic is F, calculated as mean square row or mean square column over mean square error. P-values and critical values derived from the F distribution. The table categorizes data by two factors: gender, which includes male and female, and blood lead level, categorized as low, medium, or high. Each combination of these factors forms a cell, with the response variable being the intelligence quotient score. We will calculate the mean intelligence quotient score for each cell in the table. This will help us construct an interaction graph to visualize potential patterns or effects between gender and blood lead levels on intelligence quotient scores. An interaction effect is indicated when line segments deviate from parallelism. In the intelligence quotient scores data, females with high lead exposure show lower intelligence quotient scores, whereas males with high lead exposure exhibit higher intelligence quotient scores, suggesting an interaction effect. First, test the null hypothesis that there is no interaction effect. If no interaction is found, proceed with testing row and column effects. Specifically, test for no effects from the row factor and no effects from the column factor. All tests utilize the F distribution. This flowchart explains how to interpret the interaction effect in a two-way ANOVA. First, we start by testing whether there is an interaction between the two factors. The test statistic is calculated by dividing the mean square for interaction by the mean square for errors. So the formula is F equals MS interaction divided by MS error. After calculating the F value, we check the P value. If the P value is small, for example, less than 0.05, we reject the null hypothesis of no interaction effect. This means there is a significant interaction between the two factors. When an interaction exists, we should be careful. We should not interpret the effect of one factor alone without considering the other factor, because the effect of one factor depends on the level of the other factor. But if the p-value is greater than 0.05, we fail to reject the null hypothesis. That means there is no significant interaction effect, and then we can continue by checking the main effects of each factor separately. This part is used only when the interaction effect is not significant. That means we fail to reject the null hypothesis of no interaction. So now we can continue by checking the main effects separately. First, we test the rho factor. The F value is calculated by dividing the mean square of the rho factor by the mean square of error. In simple words, we are checking whether the different row groups have a significant effect on the result. If the p-value is less than 0.05, we conclude that the row factor has a significant effect. After that, we test the column factor in the same way. The f value is calculated by dividing the mean square of the column factor by the mean square of error. Again, if the p-value is less than 0.05, we conclude that the column factor has a significant effect. So the main idea is this. First, check interaction. If there is no significant interaction, then check the row factor and column factor separately to see whether each factor has its own independent effect. We will apply two-way ANOVA to analyze performance IQ scores. Our goal is to test for interaction effects, gender effects, and blood lead level effects. The significance level is set at 0.05. The requirement check confirms that each cell's sample values are from a normally distributed population. Despite variance differences, we assume equal population variances. Samples are simple, random, and independent, categorized by gender and blood lead level, with 5 values per cell. Let's examine the StatCrunch output. This data analysis tool provides statistical results which are crucial for interpreting our study's findings. Focus on the key metrics and values presented, as they will guide our understanding of the statistical significance and relationships within our dataset. We tested for interaction between gender and blood lead level on intelligence quotient scores. The test statistic is F equals sign 0.43 with a p-value of 0.655. We failed to reject the null hypothesis, indicating no interaction effect. Thus, we proceed to test for individual row and column effect. We tested for row and column effects on intelligence quotient scores. For gender, F equals sign 0.07 and p-value equals sign 0.791, indicating no effect. For blood lead level, F equals sign 0.10 and p-value equals sign 0.916, also showing no effect. Thus, we fail to reject the null hypothesis for both factors. The analysis indicates that IQ scores are unaffected by gender or blood lead levels. Remember, two-way analysis of variance is distinct from performing one-way analysis of variance twice. Always test for interaction between factors to ensure comprehensive results. Let's explore the impact of adding 30 points to each female's performance intelligence quotient scores in example 1. This adjustment will help us better understand the method of two-way analysis of variance by observing changes in the dataset. The interaction effect analysis shows a p-value of 0.655. Since this is greater than 0.05, we fail to reject the null hypothesis. This indicates no significant interaction effect is present. The p-value for gender is less than 0.0001, indicating a significant difference in performance IQ scores. Conversely, the p-value for blood lead level is 0.906, suggesting no significant difference in performance IQ scores from blood lead levels. Adding 30 points to female subject scores confirms a gender effect on performance intelligence quotient. However, there is no apparent interaction effect or impact from blood lead levels. When sample data includes only one observation per cell, individual cell variances can't be calculated. Assuming no interaction between factors, test separately for row and column factor effects. H0 states no effect, while H1 suggests an effect exists. Using the first entry from each cell in table 12.3, we apply a 0.05 significance level to test for effects from gender and blood lead level. We assume no interaction effect between these factors. Testing the row factor of gender, the test statistic is 0.02 with a p-value of 0.901, indicating no significant effect on performance IQ scores. Similarly, for the column factor of blood lead level, the test statistic is 1.16 with a p-value of 0.463, showing no significant impact on IQ scores.